All right. So my apologies for the recording last time. So what happened was, I was going to upload it, and I listened to it, and the audio was just garbage. Like, I don't know if it was something wrong with my microphone. I don't know what the deal was, but it just, it was staticky and garbled. It sounded like my microphone was just being jumbled around in a paper bag the whole time. So as you said, I'm just not going to worry about it. So I've decided to use Panopto, which is the new sort of recording suite and whatnot. So I'm using these microphones. So I think that the audio and whatnot will get resolved. So we'll see. Okay. I'm not going to upload the attendance grades until the end of this week. Again, we've still got people adding and dropping classes, so I just thought let's just do that at the end. Your first homework assignment is assigned today. It is due at 10 a.m. via Blackboard. So just so you know, this will work the same way as it's done as I've done in previous classes. So the homework will be assigned at 11 a.m. today, and it will be due 10 a.m. Friday. And this assignment is really short. It is not hard at all. And you are definitely going to see what I mean about that when we get into it. Because ultimately what we're going to be doing is working on structural classification. Did I bring my clicker? I think I did. Oh, I'll just use keyboard. We're going to be looking at structural classification. So we're going to sort of be reintroducing you to a lot of the modeling tools that we used in statics and mechanics and materials last year, but we're going to look at it a little differently, I guess I could say. And we're also going to introduce some new aspects such as internal releases, and then we're ultimately going to look at classification. When I'm talking about with classification is I really want to answer two questions for a given structure. Is it stable, and is it statically determinate? And I actually want to explain what those mean and come up with a scientific means of classifying that. In a weird way, everything that we do for the rest of this semester is going to hinge on these questions. There's no pun intended there, even though there kind of is one there when I said hinge. You'll understand what that means later. But the way in which we analyze structures does actually depend on whether or not they are statically determinate structures or statically indeterminate structures. And so you could probably glean what that means from what we had done in Engineering 216, Mechanics and Materials, but we'll sort of formally define that a little bit better today. We'll actually have an equation that'll help us compute that. So with that, let's get into it. So the first thing I want to do is talk about, modeling and classification. Let's talk about the modeling aspect. We want to know what boundary conditions we're utilizing. We want to know about internal releases. Internal releases, for example, things like internal hinges, there are going to be actually two applications of them. The first is to represent what's really going on in the structure. There might actually be a physical hinge at a given point in a system. The other is as an analytical tool. Some of these internal releases may not actually physically exist on the structure, but we will use them as tools for certain modeling techniques. So as an example, one of the tools that we will learn to develop later on in the semester is what's called an influence line. And an influence line is a diagram that we use to assess a structure that is subjected to loads that move. Okay? What type of structure do you think that affects? A bridge, exactly. So bridges are subjected to moving loads. So how do you analyze a structure when the loads move? Okay, and so the way that we do that is we use influence lines, and in order to construct influence lines, we use internal releases and whatnot. So there are going to be uses for this, even if they don't physically exist in the real world, we still might need them. Okay, so let's talk about the modeling aspect first. Okay. So, from the last lecture, remember the idea that I wanted you to have present in your head, just at least in the background as we go through a lot of these problems, is that structures are complicated. They are three-dimensional, dynamic, nonlinear systems, and if we really wanted to start getting down into the weeds of analyzing a structure, we can get real complicated with things. I mean, I know there's a couple people in here that might have some experience with some refined 3D, finite element techniques. I mean, you can go really nuts with trying to represent behavior, but there's a computational expense to that. I mean, the more difficult you make your analytical model, the harder it is to analyze. And then you ask yourself, is it really necessary? As an example, here's a roof truss, right? So I'm going to simulate these roof trusses with a two-dimensional plane truss analogy that might look something like this. So there are assumptions baked in to this structural behavior. And those assumptions sacrifice some accuracy. As an example, one of the assumptions that we make in truss analysis is that the members only carry axial load. They're either only experiencing tension or compression. That's it. No bending moment, no shear, none of that. Now, in strict honesty, that's not 100% true. There's always going to be a little bit of shear, a little bit of bending moment, even if it's a truss. But is it worth it? I mean, is it worth it to really consider it? If you consider shears and moments in this structure, suddenly this becomes highly indeterminate, and suddenly it becomes very difficult to analyze by hand. But is it really going to affect the size, the selection of your, poplar elements in your roof? Probably not. Whether poplar, Douglas fir, number 2, Georgia pine, what have you. In the end, we are engineers, and it is our job to spec out the dimensions, size, and details associated with this system. And that's what we need to do. I guarantee you a plane truss analogy will work just fine for a system like this. But you do need to recognize that with these assumptions, there is a slight cost of accuracy. So just keep that pushing in your head. So example modeling, not just from the mechanical assumptions, is from the geometric assumptions. So, for example, it's very common in structural analysis to take a three-dimensional bridge and represent it as a two-dimensional model. I'll go ahead and tell you, in this class, we will primarily analyze structures that are two-dimensional. We won't really get into 3D land. That doesn't mean structural engineers don't do that or don't have to consider, the third dimension. We do. But we can usually handle that through approximate techniques like tributary area. In bridges, we can utilize live load distribution factors, and so on and so forth. And it's, this is what we do in practical engineering. So I'll go ahead and tell you, no IJK in this class. We're not doing it like that. In fact, we're going to revisit how we sum forces in some moments from the get-go. And you're going to find that the approach that we use is a lot easier. If you want to have a simple explanation for what we do in this class, we take what we did in statics and mechanics and materials, and we develop simpler ways of doing it, but we just analyze more complex structures. So that's kind of the goal of what we're doing here. Okay. Boundary conditions. Now, boundary conditions are what attach the structure to the ground. And what I mean by the ground could mean the actual ground, or it could mean the next adjacent structural element. So, have you seen this before? This is right up here. This is the canopy that connects the old engineering building to the new engineering building. And what I've got here are two arrows. Let me use my little Control L. Oh, that doesn't work on this. Well, that's okay. So let's look at these two boundary conditions here. So what I've got here is, let's look at this one below. Okay, so this is where the boundary condition connects to the ground. Okay, so if I was designing this column, I would need to define a boundary condition here, and the answer, or the question might be, is this going to be a simple boundary condition? Is it going to be a fixed boundary condition? We'll talk about specifically what that means here in a little bit. But this would be an example of a boundary condition connecting to the ground, right? Whereas up here, okay, so let's take a look at, let's say, this beam, okay? If I'm designing this beam, I might design it as a simply supported beam, but the ground, the boundary conditions, are not the physical ground. It's whatever the connection criteria are connecting it to the next adjacent element. So when we analyze structural systems, we tend to do what's called a load takedown, and the idea is it's sort of like a hip bone connected to the leg bone type of thing. So we have load that goes from the beam, the load from the beam goes to the column, the load from the column goes to the ground. And so later on in the semester, we will actually perform load takedowns using tributary area and whatnot, so you can kind of see how that goes about. But in terms of identifying the types of boundary conditions that we use, this is probably where we're starting to get a little bit more familiar to what you've done in statics and mechanics of materials and what have you. So there are really three main support conditions that we utilize as engineers. So the first is pin supports. So pin supports are those that restrict translation but allow rotation. Okay. So what we find is that if we look at the reactions, we end up getting two unknown reactions, one in the X direction, one in the Y direction, but we don't get moment. These tend to allow rotation. Now this is sort of a real world example of a pin boundary condition. This one is as well. And this one up top, you might go, wait, what? Like, is that a pin boundary condition? And analytically, yes, we would treat that as a pin boundary condition. The reason why is because whenever we're looking at steel design, a very basic way of explaining some of the mechanics is that we tend to assume that the web of the I-beam transmits the shear and the flanges of the I-beam transmits the moment. Okay? And if we look at these connections, we see that the flanges, the up and bottom portion of the I-beam, are not connected to the column. It's just the web. So the idea is that we would assume that this connection transmits shear but not moment. Hence why we would probably idealize it as something like this. I will probably draw this as a triangle. You might see something like this in the textbook, but that's going to basically be the definition of our pin boundary condition. I get the feeling at this point I'm starting to get into more familiar territory. Am I right? Okay. Roller supports. These usually only restrict motion in the direction of the roller. So one of the things that we didn't deal with in statics and deformables, which we will deal with in here, are inclined rollers, because that is a possibility as well. They only develop a reaction in the roller's direction. And to be clear, there are examples of this in the real world. One of the examples I always like to use in bridges are fixed and expansion bearings. So the idea is that, so if we're talking about a bridge, let's say in West Virginia, in the summer, we can hit 90 or even triple degree weather, but in the winter, we can get well below freezing. So that's a hell of a temperature differential, and bridges will expand and contract under different thermal loadings. Well, we have to have one of the bearings or one of the support conditions to allow and be able to receive that thermal expansion and contraction. Otherwise, you can get a heck of a lot of external thrust being applied to your support condition. So it is very common to have one bearing that is fixed, that keeps the bridge in place, but the other that allows a little bit of movement along the span. So a hinge roller boundary condition does actually have some very real-world analogies. Now, if you ever hear me use the term simple supports, okay, what I mean by a simple support or an element that is simply supported, I'm talking about pin and roller supports. And the reason why I'm lumping those together is because pin and roller supports do not resist moments, okay? Whereas a fixed support, something like this, does resist moments. So analytically, you will sometimes find that I lump pin supports and roller supports kind of together. And so if you ever hear me refer to a simply supported beam or simple supports, that's what I'm talking about. I'm talking about a pin and roller situation. Fixed supports, however, transmit both shear and moment. And what you will find in the real world with fixed supports is either a degree of encasement. So if we're talking about reinforced concrete, literally the beam and the column being cast together, or an element being encased or embedded in a given element. Or in the case of steel design, you will find a connection scenario where both the web and the flanges are connected. So for example, this is a column base plate, and you can see that weld is being transmitted along both the web and the flange. So this connection would be designed to transmit both shear and moment. Okay, so that's analytically and physically, those are really the differences between those two systems. Everybody okay with that? Any questions? Okay. Now, let's talk about internal releases. So an internal release, when I say an internal release, what I'm basically saying is that I'm relieving a response at a given location. So, for example, if here's a table and I sit on this table, I am bending the table. The table is developing internal shears and moments. But if I place a release at a given point, a very common one would be a hinge. The idea is that at that particular point, I know what the internal moments are. If it's a hinge, the internal moments are 0. Okay. Now, there are physical analogies of this. Has anybody ever seen a bridge connection that looks something like this? Have you ever seen this before? This is what's called a pin and hanger connection. Okay, and this connection is specifically fabricated and designed to transmit no moment. Now, if you want a reason for why these connections even exist in the first place, beyond just ease of construction, because they are a whole lot simpler than current splice connections that you see in bridges nowadays, they actually made the bridge easier to solve analytically when they were designed in the first place. I mean, a lot of these bridges were designed, you know, in the 40s, 50s, 60s, where slide rules were still pretty prevalent, right? We didn't have, you know, computational masterpieces on our iPhones and whatnot that can do all the math necessary needed to be done. I mean, these were days when the math was still done by hand. I mean, really done by hand. So actually inserting a hinge made the structure solvable by hand. And I might actually be able to glean a little bit of insight on that today. Now, when I do this in class, I will probably draw my hinge either like this, or I know in the slides I probably just do something like that. If you ever see a white circle on the structure, that sort of represents a hinge. So, like for example, if I was looking at this connection, like if I had this type of connection in a building structure, I would treat that as a hinge because it's transmitting shears, but not moments, because the flanges are not connected. Does that make sense? All right. Any questions so far? Again, don't hesitate if you got questions, please. This is fun stuff. Okay, so in terms of modeling, what I'm really after right now is to just make sure that you understand the boundary conditions that we utilize in order to assess a given system, or to model a given system. Now I want to talk about classification. So what I mean by classification is I want to take a structure and I want to ask two questions. Is it stable and is it statically determinate? So let's talk about what exactly those mean. Okay. So our best friends from Engineering 213, right, are equations of static equilibrium, the sum of forces and the sum of moments. Now, if you remember from Engineering 213, if we're talking about 3D land, we have 6 equations of equilibrium in 3 dimensions. We have the sum of forces in X, Y, and Z, and then the sum of moments in X, Y, and Z. So if you remember from statics, you know, the fundamental equations of statics were that the sum of forces must be equal to 0. And that's good, great, grand, and wonderful if all the forces all meet at a common point. Once they stop meeting at a common point, you exit the land of particle statics, and then you get into the land of rigid body statics. And in rigid body statics and non-concurrent force systems, your system must also respect that the sum of moments equals 0, otherwise it will rotate. So that's why we have sum of forces and sum of moments. Now, in 2 dimensions, we can idealize that to just deal with that the sum of forces in the x direction must be equal to 0, the sum of forces in the y direction must be equal to 0, and the sum of moments must be equal to 0. So everything rotating this way has to equal everything rotating this way. And those are really the 3 equations that we need to deal with. Now, I want you to keep that number in your head right now, the number 3, okay? Because that's a very important number, okay? Talk about the number 3. Here's a problem. I have a beam. What type of beam is that? Well, I'm going to say it's simply supported. Simply supported because I have a hinge roller boundary condition, right? So there's some of the terminology for you. Now let's go back to statics land. Okay, so I have 2 reactions over here at the left because that is a pinned boundary condition. And so I have an unknown reaction in the x direction, an unknown reaction in the y direction, right? 2 reactions there. What about over here? Okay? 1 vertical reaction, because it's a roller. So I have how many unknowns? 1, 2, 3. Okay. So there's 3 unknowns. Well, how many knowns do I have? How many known quantities do I know? How many equations of equilibrium do I have? I have 3. I know that the sum of forces in the x direction equals 0, the sum of forces in the y direction equals 0, and the sum of moments equals 0. There's that pesky number 3 that keeps popping up. So the way I've categorized this here in this table is I have 3 unknowns and 3 knowns. My 3 knowns are the equations of equilibrium. My 3 unknowns are my 3 reactions. And this should start jogging your memory a little bit. Like, For example, what is that? Let's see if y'all remember that. What is that? Zero, right? And how did you do that? Well, you said, okay, the sum of forces in the x direction must be zero, and there's nothing going horizontally. So if there's nothing going horizontally, that's got to be zero, right? And so, like, how would you determine, let's say, by?
Pick your rotation point at A.
Yep.
So you make your AY 0 with the moment due to the force.
Exactly. So you would sum moments, referencing A, and figure out how much moment needs to come from here to cancel out the moments over there, right? So you're using this equation to solve for that one. You're using this equation to solve for that one. And then when you have this, plug it into that, right? 3 equations, 3 unknowns, boom, system solved, right? Make sense? This is a system that is statically determinate, okay? And that's really the key issue here. It doesn't just extend to external reactions. This also works for internal response as well. Remember, secret weapon of structural engineering is a samurai sword or a lightsaber if you are a sci-fi fan. If I'm sitting here on this table, I am generating internal response inside this table. If somebody comes over here with a samurai sword or a lightsaber and cuts through the table, I'm going to have a bad day and their grade's going to suffer. It's a joke, not a very funny one. But the reason why is because inside the table right here, there is internal response being developed. An unknown force in the x direction, an unknown force in the y direction, an unknown moment. What I can do is I can cut a section, look at either component of the structure, and say, okay, I've got 3 unknowns. An unknown internal axial force, an unknown internal shear, an unknown internal bending moment, and then I can solve for those unknowns, again, utilizing my equations of equilibrium. Sum of forces in the x direction, sum of forces in the y direction, sum of moments at the cut of the section equals 0. 3 equations, 3 unknowns. So this procedure, this idea, not only works to develop our external support reactions so we could solve for those, let's say if there were 8 or 24, we could also determine the internal response at a given point. Okay? That idea is what's called static determinacy. Okay? If we can perform the analysis using only the equations of equilibrium, the system is determinate. Now, if there are more unknowns than there are equations of static equilibrium, then the system is indeterminate. And do we deal with structures that are statically indeterminate in real life? Oh, you bet. We do that all the time. Take a bridge that has a solid beam, put a pier in the middle. Indeterminate, okay? We do that all the time. That's a very simple example of indeterminacy. This building, for example, the moment frame that withstands the wind and seismic, well, not seismic, but wind load here in Huntington, that structure is highly indeterminate. And so you're in one right now. Now, so if the number matches, if we match the number of unknowns to the number of knowns, so if we can solve our problem using equations of equilibrium, then the system's determinate. If we have more unknowns, the system's indeterminate. But what if we have less unknowns? If we have less unknowns than we do equations of static equilibrium, the system is unstable. And I've got some very clear examples to show you what that means. When you see it, you'll go, okay, I get it. I see some folks writing, so I'm going to give you a sec. Everybody good? Why is that popping up? Okay, so now what I want to do is I want to show you a rigorous means of computing and actually determining the degree of external indeterminacy. So I'm going to call it indeterminacy, and I'm going to call it I sub E. And I'm going to call it, that's the degree of external indeterminacy. So it stands to reason that later on we are going to have internal indeterminacy, okay? And we're going to have internal indeterminacy because we're going to look at whether or not trusses are internally determinate or not, whether beams and frames are internally indeterminate or not. And the way that we compute that is we use this formula right here, okay? So we take R minus the quantity EC plus 3. There's that pesky 3 again. Where's that 3 come from? Well, it's, by golly gosh gee, it's the number of equations of equilibrium. If you want to know where this equation comes from, this equation, let me see if this works here. This equation is essentially the unknowns minus the knowns. Like, if you really want to know what this is, it's just a fancy way of categorizing that. So, the knowns. Let's talk about what the knowns are. The knowns is this quantity EC plus 3. Whenever we do a 2D structural analysis, whenever we perform that analysis, there's going to be three things that we know. The sum of forces in the x direction equals 0, the sum of forces in the y direction equals 0, the sum of moments equals 0. So there are three known quantities. The other known quantities are going to be what are called the equations of condition. And basically that's however many internal releases that we have. So if we have a structure that has a hinge, has one hinge, E sub c is going to be 1. Because we know what the internal response is at that hinge. Okay? So the known quantities are 3 plus however many releases that we have. The unknowns are the reactions. So I'm calling that little r. Okay, so all I'm doing is I'm comparing the number of unknowns to the number of knowns. So IE equals r minus the quantity EC plus 3. And the other equations that we develop later for trusses and the like are going to be in the same format. The number of unknowns minus the number of knowns. Now, note, again, so if this equation is 0, if it equals 0, then the number of unknowns and the known knowns match, and the structure is statically determinate. Okay? If the equation is bigger than 0, I'm going to say it's statically indeterminate, and if it's less than 0, it's unstable. But there's a little fine print here. Okay? I say if IE is 0, the structure should be statically determinate. If I say IE is greater than 0, I say the structure should be statically indeterminate. This box here is actually pretty important. It says a non-negative value of IE does not guarantee that a structure is stable. It is very possible that you have a structure that has oodles and oodles of support reactions and it's still unstable. Okay? Very, very possible. Okay? And I'm going to show you some very easy to understand examples of that here in a bit. Everybody got this? Okay. Oh, I need to turn it down. Okay. So let's look at some examples. Okay? Let's look at this structure right here. So if I do the math, okay, well, first off, if we look at all of these structures, none of these structures have any internal hinges. They don't have any internal releases or anything like that. So we're going to say E sub c equals 0 for all of them. So let's look at the very first structure. So the very first structure, there are 2 roller supports, so there's 2 reactions. And if I just plug and chug into this formula, the formula states that 2 minus the quantity, 0, plus 3, or 0 minus 3, that's negative 1, so the structure is unstable. So, to be clear, if IE is negative, the structure is unstable. But there's also very clear physical reaction, or physical connotations to that as well. Look at this structure. Isn't that a skateboard? If I take this structure and apply a lateral load, if I push it, is there any way that the structure can resist it? No, it's just going to boop. It's just going to go. So this structure is not statically stable because it cannot resist that lateral load. Make sense? So that's why when you have a negative value of I, the structure is unstable, because it doesn't have the means to resist loads in certain fashions. Okay? This structure is stable and it's statically determinate. Now I'm telling you this structure is stable and I'm telling you this structure is stable. Here in the next slide, I'm going to help you define why that is. But from the maths perspective, if I have 1, 2, 3 reactions, no equations of condition, I have an I value of 0, the structure is stable and statically determinate. Now, this structure here, this one's kind of special. Okay, so I've got 1, 2, 3, 4, 5 reactions. So my R is 5. So if I plug into this expression here, R is 5, this is 0, 5 minus 3 is 2, I is positive. So we're going to say that structure is stable and statically indeterminate. And when we refer to that, we typically say that that's statically indeterminate to the second degree. So if I was 58, it would be statically indeterminate to the 58th degree. Okay? So whatever the I value is, that's the degree to which it is indeterminate. The higher that I value is, the harder it is to solve by hand. That's kind of like why we refer to it that way. Make sense? You mean hang out for a sec, or are you all good? Okay. Now, I keep saying that a non-negative value of I does not guarantee stability. What do I mean by that? This is what I mean by that. For a structure to be stable, you have to have 3 conditions. Okay, the first condition is that your I has to be non-negative. It has to be either 0 or positive. But the other 2 is that the support reactions can't all be concurrent and they can't all be parallel. So for example, look at this structure right here. Now if I just compute the I value right here, I have 4 reactions, 0 equations of condition. I get an I value of 1. But that structure is not stable. It's another skateboard. If I apply a lateral load, it's just going to go. Right? So, just because I is positive does not mean the structure is stable. And to be clear, whenever we do these classifications, if the structure is unstable, it's unstable. I don't care what degree of indeterminacy is, I couldn't care less. It's not stable. That's key to us because we're not building any unstable structures. Hopefully. Now, what about this structure down here? I argue it is also unstable because here I said concurrent on this upper one. I'm sorry. Here the reactions are parallel. On this one down below, the reactions are concurrent. Okay? These reactions, all of the reactions, every reaction in the structure all meets at a common point, okay? And what that means is that this structure is kind of like a wheel. If I take this structure and turn it, it cannot resist that. The rollers only resist reactions in the direction of the roller. If I rotate it about this central point, the structure is unstable. It can't resist it. Which that didn't happen on these previous slides, right? If you go back to these previous slides, if I look at this structure here, we didn't have a situation where the reactions were all concurrent or all parallel. I mean, this one, is not parallel with that one, and these two aren't concurrent, so yeah, that's stable, right? Does that make sense? Everybody okay with that? So, the last thing I want to show you is what happens with equations of condition. So, equations of condition serve to reduce your indeterminacy. So, if we look at this structure right here, let me use my pen here for a second. Let's look at this structure. So, this structure is indeterminate. It is stable and indeterminate, and it is indeterminate to the second degree. Okay? If I throw a hinge in there, so let's say I put a hinge right here in the middle, okay? What that does is that increases the EC value by 1, so where it was a statically indeterminate structure to the second degree, now it's an indeterminate structure to the first degree. And so if I throw 2 more hinges in, boom, it's stable and statically determinate, because I can utilize the internal response at these points to solve for the reaction, something I'm going to show you how to do later. Any questions?
That's what you're talking about with the hinge and the bridge.
Yes,
and that's what makes it solvable by hand.
Yes, and this is one of the reasons why older steel bridges you might see, that are multi-span might have pin and hanger connections. This is one of the reasons. The other, it is actually easier to fabricate and construct, but this is a big reason for it. Let's actually do a few. Like, I'm just showing you a bunch. Let's actually do a few. So, let's do that. So, I've got a few examples for you. Okay? So, we're going to do these together. Okay? So, let me pull this up here. All right. So we've got a series of examples, and I'm doing this in our OneNote. So if you're able to access that outside of class, you'll see that everything I'm about to write here will be present on the OneNote. So let's do each of these examples one at a time, and let's see what we can do with our classifications. Okay, so let's start off with example 1. So the first thing I'm going to do is I'm going to write down or identify the support reactions. So let's start right here. This is a pin supports. How many reactions do I have? 2, and this is 1. This is 1. So I'm going to have a reaction here, a reaction here, reaction there, reaction there, right? So for this one, I might say R is 4, right? Now, what about EC? Are there any internal hinges on this structure?
No.
No. So therefore, my 3 dots for therefore, IE is R minus EC plus 3. Which is 4 minus 0 plus 3. 4 minus 3, which is 1. Now, the other question that we should ask is, do we have a situation where all the reactions are parallel? No. Do we have a situation where they're all concurrent? No. So I would argue that this structure is stable and statically determinate, and I would say it's to the first degree.
Determinate or indeterminate?
Sorry, indeterminate. Indeterminate. I'm sorry, you're right. Remember, Marshall policy says I'm allowed 7 mistakes per semester, but I'm the one who keeps track of the mistakes, so it's a corrupt system. I know. That was a joke. I'm a dork. Okay. Yeah, so that's stable and statically indeterminate to the first degree. So just to give you a highlight on how this works analytically, we cannot use just the equations of statics to analyze the structure. We need more info. Okay, and so if you want a abstract thesis statement for how structural analysis works for indeterminate systems, what we do is, there's a couple ways of going about it, but essentially what we do is we exploit the relationship between forces and deformations. Let me give you a simple example. What's the deflection right there at this support? Say it again?
0.
0. There's your fourth fact. You see what I mean? So one of the types of approaches are what are called flexibility approaches. We identify a redundant reaction and we say the deflection there is 0, right? So what we do is we say, let's compute what that deflection is, assuming that support wasn't there. And so let's say it's 2 inches. So figure out, well, how much force is required to push it up 2 inches? And there's your reaction. So, but in order to get there, we got a lot of stuff to talk about. We got to figure out, how do you analyze it? How do you compute the deflection? So that's why we always start with determinate analysis. Okay. So far, so good? Okay. Example 2. So we've got, let's look at these supports. How many reactions do we have for each of these supports? 3, because they're fixed supports. So we have X, Y, and moment. So okay. So we have R is 6, because we have 6 reactions. But how many equations of condition are we going to have? 3. So if we compute, we get 6 minus 3 plus 3, and we get 0. Now, do we have a situation where all the reactions are concurrent or all the reactions are parallel? No. So this structure is stable and statically determined. What about example 3? Okay, so let me scroll down a little bit. So example 3, we've got rollers, right? What's the story? Say it again. They're all parallel, which means that structure is unstable. That structure is unstable. Don't even bother doing any math. I don't care what I values. It doesn't matter. It's unstable. So what you can do for this problem is say all reactions are parallel. Therefore unstable. Boom. And so finally, we can look at this one. I want you all to mess with this one, but tell me what you get for this. Yeah, you all work on this one. So we've got fixed supports here and then 2 hinges. Anybody got an answer?
Stable and statically indeterminate to the first degree.
Okay. I think you're right on that because, let's see, we've got 1, 2, 3, 4, 5, 6. And so R is 6. EC is going to be 2. IE is 6 minus 3 plus 2, which is 1. So yeah. Which, by the way, if my handwriting is atrocious, go ahead and tell me. I will take it against you, but still tell me. That again is a joke. All right. And that's it. Pretty simple, right? All right. So, I'm just curious, any questions on these examples? If you can do this, you can do the homework assignment, because the homework assignment is just more of these. I'll just tell you. I gave you 5 of them. All my homework assignments are worth 10 points, so it's just 2 points apiece. And, I mean, think about like how long it would take you to do this. These aren't hard. These are pretty short problems. So, the idea is that, again, with my homework assignments, they're not intended to be time crunchers. And to be clear on that, some of the problems and some of the methods that we do in this class, they are long, and there's no way around it. And for some of those homework assignments that are going to get long, they get split over a couple days. Like I don't just say, oh, you have it due Wednesday because Dr. Mike can't get out of his routine. I mean, we have some buffers built in for some of those longer assignments. So. Sound good? Yes.
When it's indeterminate, how do you know if it's first degree or like?
Whatever this value is.
Okay.
Yeah, whatever the I value is. So if I is 64, it's to the 64th degree. Yeah. And again, this will become clear as we start getting into that realm later, but the higher that value is, the harder it is to solve, which is why it's important to characterize that. Most of what we do this semester is going to be problems where I is 0, okay? The reason why is 1, we try and keep it simple in civil engineering whenever we can, but 2, even if you do have an indeterminate system, you analyze an indeterminate structure, utilizing principles of determinant analysis. You've got to master determinant analysis before you even have a chance at indeterminate. So the plan is for me to offer a special topics class next semester on advanced structural analysis, and we'll probably spend most of the time looking at indeterminate structures. So it'll be fun. So, any questions? That's all I got. I will see you all on Friday. Hopefully the audio has come through a little more clearly on this. I'm feeling better about it.